Welcome to the third lecture of this week. Today we will talk about analyzing this composite laminate using the energy or virtual work principle with first order shear deformation incorporated. So, previously we dealt with classical laminate theory and we have done the energy formulation for static problem as well as the vibration problems. Here we will do the similar thing, but we will incorporate the first order shear deformation here. So, for that we will again start with Hamilton's principle, and the principle says that the integral between T1 to T2, the integral of delta T, where T is the kinetic energy, U is the strain energy and W is the work done by the external force. We can just call it W. Sometimes we put E just to denote that it is the external force, and that integral is 0. So, T is kinetic energy, U is strain energy, and W is work done by external force or applied force, external force or external load. Now, let us look into this del T term first. So, we have a term like T1 to T2, integral from T1 to T2 delta T, T is equal to 0. Now, here T1 and T2 can be any time step, any time instance. So, this integral is not valid for some chosen time instance. So, T1 T2 can have any value and the integral has to be valid for that. I mean, this relation has to be valid for that, the integral is 0. Now, let us look at this first. So, delta T is equal to we have T1 to T2 and delta T is kinetic energy, and kinetic energy is we know the volume integral of kinetic energy densities, and the kinetic energy densities are we are going to define now. So, we have half rho and then U dot square, this is kinetic energy corresponding to motion along direction x, plus half rho V dot square plus half rho W dot square, and we integrate it along the we integrate it through the volume V, and its variation is here. So, it is delta T, and let us keep rest of the terms as it is, T1 to T2 delta U plus T1 to T2 delta W dt and everything is 0. Now, if I take this variation inside, then T1 to T2, then we have V. If I take this delta inside, we know that from the property of the variational operator that rho U dot square is equal to rho U dot into delta of U dot. Then we have plus rho V dot into delta of V dot, and then we have plus rho W dot into delta of W dot, and we take the volume integral of it and minus, and this is integral dt, and then we have minus T1 to T2 delta U dt, T1 to T2 delta W dt, and total is it is equal to 0. Now, these integrals these differentiations here U dot V dot W dot, they are all time derivatives, and we have an integral over time. So, we can do integration by parts and shift the time derivative from the variational part to the actual variable part. So, what we do here is we write V U dot delta U plus I mean the V means volume integrated over the volume, the integrand is rho u dot delta u plus rho v dot delta v plus rho w dot delta w volume integral, and this thing is evaluated at time instant t1 and t2, the end time instants, and then integral from t1 to t2 we have volume integral of rho u double dot delta u plus rho v double dot delta v plus rho w double dot delta w integrated over the volume and then integrated over time. And then we have minus T1 to T2 variation of u, its integral over T1 to T2 plus we have integral from T1 to T2 of variation of w, and then this entire quantity is 0. Now, if I look at this and this, we can see that the first term is defined only at the two end time steps T1 and T2, whereas rest of them is integral. So, whatever the value of these quantities you use V's W's in between T1 and T2, that does not affect this, and I am saying that this entire expression should be 0 for any arbitrary choice of T1 and T2. That means that this quantity should be individually 0, and rest of it whatever we have here, that should be separately 0. And again if we look at rest of these quantities, they are integral from T1 to T2, and the limit of the integration T1 to T2 are arbitrary. That means that the integrand should be 0. So, since T1 and T2 are, or we can write it, since it is valid for any T1 and T2, we can say that the quantities here inside the time integral should be 0, that means the integrand should be 0. So, that tells me that rho u double dot into delta u plus rho v double dot into delta v plus rho w double dot into delta w dv plus volume integral of variation of strain energy minus the work done by the external force. So, minus del w should be 0. Yes. So, here we do not really need to write the volume integral, because capital U itself is the strain energy, not the strain energy density, and similarly here del w, and that should be 0. Now, what we will do is we will first look into these terms separately, and then we will talk about this and this. So, now let us look into this. So, we have here volume integral of, so this term is here. So, you have volume integral of rho u, as we know it is u 0 double u. So, u double dot is u 0 double dot plus z into psi x double dot. So, we have already discussed that u is equal to u 0 plus z into psi x. So, u double dot is u 0 double dot plus z into psi x double dot, and then we have variation of u 0 plus z into psi x, its volume integral. Then we have the volume integral of rho v 0 double dot plus z into psi y double dot, and then we have variation of v 0 plus z into psi y volume integral, and plus we have volume integral of V into W double dot into variation of W. Now, what we will do is we will convert this volume integral into surface integral. So, what we will do is first we will integrate over the thickness of the laminate and then we will integrate over the surface. So, we have surface integral first and integration over the thickness, and we know that laminate is made of n number of layers. So, k goes from 1 to n, total n number of plies. Along each ply we integrate from zk minus 1 to zk, and then we have rho u0 double dot plus z into psi x double dot multiplied by variation of u0 plus z into psi x dz d omega. So, we have a laminate like this, it is made of total n number of layers, say, and its entire volume is denoted as V, and then we denote its surface as omega and the thickness with several layers. We have already discussed it, Z0, Z1, it goes up to Zn. So, for kth ply, the Z ranges from Zk minus 1 to Zk. So, this is x, this is y, this is z. So, this is x and y and this is z. So, we integrate over the thickness first and then we integrate over the surface. Then we have the same thing for the second quantity, and for that we get summation k from 1 to n summed over all the plies zk minus 1 to zk rho k, because rho can be different for different layers. So, we put a subscript k, we can do this also here. That is just to differentiate the row between rows at different layers, and then we have z into psi y double dot, and then we can write a variation of V0 plus z into psi y, and then integral over z, integral over omega, and we can write the last term also in the same way, k is equal to 1 to n zk minus 1 zk rho k, and then we have w double dot variation of w dz d omega. Now, if we look at here, so rho k into u0 double dot into delta of u0, if I integrate it, u0 double dot and delta of u0, they are not functions of thickness, but rho can be a function of thickness. So, if I integrate this density over the thickness and sum it up, we get mass per unit area, and that we call as I0, that we discussed while dealing with this same formulation using classical laminate theory also. So, we get I0 and we have u0 double dot into delta of u0, and then if I just multiply rho k into z sigma x double dot and then multiply with delta of u0 and integrate, we get I1 into psi x double dot, and both the terms have delta u0 in common. So, because we have z here, z into rho k integrated and summed up gives me I1, and this is d omega, and then here we have Now, let us take this term common and multiply with this, and that will give me I 1 u 0 double dot plus I 2 psi x double dot into variation of psi x d omega. So, if I multiply this z psi x double dot into with z psi x, we get z square, and z square into rho k on being integrated and summed up gives me I 2. Similarly, from this term we get I 0 v 0 double dot plus we have I 1 into psi y double dot multiplied by variation of v 0 plus we have I 1 into v 0 double dot plus I 2 into psi 2 double psi y double dot multiplied by psi y, and then we integrate over the surface, and then finally we get the result of this integration. So, it is integral of rho k over the thickness, and that gives me I 0, and we have w double dot multiplied by variation of w. So, this is the final expression of this is this, and now we will evaluate rest of these two, and then we will combine everything. Now, so let us look into this now. So, we have this as delta of u and this as delta of w. So, delta of u means the variation of the strain energy. So, we that is the internal virtual work, and we know how to write that, that is stress multiplied by the virtual strain, and we integrate that over the volume. Now, previously in classical laminate theory we had 3 non-zero stress components. So, there were 3 components of this delta u, but here we have 5 non-zero stress components, we have these 2 added stresses also. So, we have total 5 components here. So, these 3 we have already dealt with, now we are just adding these 2. So, for this we know that sigma x is equal to delta of sigma x is equal to sigma x is put here, and delta of epsilon x is equal to delta of epsilon x 0 plus z into kappa x. Now, kappa has a different definition here, previously it was minus of del 2 w by del x 2, here it is del psi x by del x. Similarly, we have sigma y into delta of epsilon y. So, for that we write sigma y into variation of epsilon y 0 plus z into kappa x, and z kappa y, and kappa y is del psi y by del y, and in the third term we have z into kappa s, and that is del psi by del y plus del psi y by del x. Now, in all these cases it was a volume integral. So, we integrate them over the thickness and sum it up, and then finally we integrate them over the surface. So, that is what has been done here. Now, we have tau x z multiplied by delta of gamma x z. Now, gamma x z has no kappa component. So, gamma x z is equal to gamma x z 0, and we know that is del w by del x plus psi x. So, this is del w by del x plus psi x, we already discussed it in last class, and similarly here we have tau y z into gamma y z, and this we know this is del w by del y plus psi y, and again we integrate them over the thickness, sum up, and then we integrate over the surface, and then we have the external work done by the external force subtracted. So, the external force is distributed over the surface. So, it is a surface integral force multiplied by the variation of displacement along z direction. So, delta w. Now, if I look at this term sigma x multiplied by delta of x 0 and integrate. So, sigma x gets integrated over the thickness and summed up. So, that gives me n x. Similarly, here after that sigma x multiplied by z into variation of kappa x. So, sigma x into z gets integrated, and that gives me m x. So, here we have m x into variation of del psi x by del x integrate over the surface. Now, previously we had a negative sign here in the classical laminate theory, because psi x was equal to minus of del w by del x, but here because the definition has changed. So, we do not have the negative sign here. Similarly, we get here ny into variation of del V0 by del y integrated over the surface, and here we have my into variation of del psi y by del y integrated over the surface. From the third term we get ns into variation of del u0 by del y plus del v0 by del x integrated over the surface, and we get when we multiply sigma s into z we get ms. So, we have integration of ms into variation of del psi x by del y plus del psi y by del x. Now, when we integrate tau x z over the surface, we get Vx, and so we get Vx multiplied by del w by del x plus psi x its variation, and similarly here we have Vy into variation of del w by del y plus psi y, and this term comes as it is. Now, one thing to note is that we incorporated the in the definition of tau xz itself we have incorporated the shear correction factor. So, we are not writing it separately, and similarly here also. So, what we are considering here is tau xz tau yz is equal to the shear correction factor multiplied by the Q matrix corresponding to the transverse shear xz, gamma xz, gamma yz. Now, if I combine all the terms whatever we derived here and here and putting it into the Hamilton's principle, so then the equation looks like this. So, finally, this is the expression of Hamilton principle after incorporating the shear deformation. Now, our job is to make assumptions for u0, v0, w, psi x, psi y. So, here we have 5 variables u0, v0, w, psi x, psi y. Previously it was only u0, v0, w, now we have 2 more variables psi x and psi y. So, we assume them like this, and these assumptions should, we know that they should satisfy the essential boundary conditions, it homogeneous version. If we can satisfy natural boundary condition, it is good, but that is not a requirement. So, u0 is written as this. So, these are the functions that we approximate for u0, this is we approximate for v0, this is something we approximate for w, and we have seen this before. The new terms are psi x and psi y. The same procedure goes, we assume some functions for psi x and assume some functions for psi y. Now, for u0 we are using L number of terms, for v0 we are using m number of terms, for w using n number of terms, for psi x we are using p number of terms, and for psi y we are using q number of terms. Now, L, m, n, p, q they can be same also and they can be different also. So, keep it more generic, we are using different values for them, we are assigning different variables. Now, if I put everything in this equation, then we can write this equation. So, this entire expression, so if we subtract these approximations in this equation that we get from the Hamilton's principle, then this entire expression is in terms of a uj up to a psi yj and delta a ui up to delta a psi yi, and then we know that we can separate the terms associated with delta AUI, delta AVI, delta AWI, delta A psi xi, delta A psi yi, and separately we equate them to 0, and that gives us total 5 simultaneous equations. So, we follow the same procedure that we followed for the classical laminate theory, only thing is that we have to incorporate these and these also. So, if we do that, the final set of equations that we get are this. So, we have from coefficient of delta AUI equal to 0, that gives me a equation which looks like this: I0 into U0 double dot plus I1 into psi x double dot multiplied by phi ui plus nx into del phi ui x by del x plus ns into del phi ui by del y, and this integral is 0. So, that is the, so this gives me total L equations, and then coefficient of delta A V I equal to 0, and that gives this equation I 0 V 0 double dot plus I 1 psi y double dot multiplied by phi V I plus we have n s into del phi V I by del x plus n y multiplied by del phi V I by del y, and this integral equal to 0. So, this gives me total m equations, and then we set the coefficient of delta A W I to 0, and this gives me this equation. We have V x multiplied by del phi W I by del x plus V y multiplied by del phi W I by del y minus q into phi W I plus I 0 into W double dot multiplied by phi W I, and this integral is 0. So, this gives me total n equations, and then if we take the coefficient of the variation of the unknown associated with psi x to 0, this gives me this equation I 1 into u 0 double dot plus I 2 into psi x double dot into phi psi x I plus m x multiplied by delta del of phi psi x I by del x plus we have m s into partial derivative of phi psi x I with respect to y plus V y into psi x I and integral of that equal to 0, and this gives me total p equations, and then we set the coefficient of delta A psi y I to 0, and that gives me this equation I 1 multiplied by V 0 double dot plus I 2 multiplied by psi y double dot into phi psi y I plus m s multiplied by del phi psi y I by del x plus my multiplied by del phi psi yi by del y. One correction here, this is V x, not V, this is V x, and then we have plus V y into psi y I multiplied by this entire thing integrated over the omega, and that is equal to 0, and that gives me total q equations. So, we get total L plus M plus N plus P plus Q equations, and we have that many number of variables. Previously the number of equations was L plus M plus N, and the number of variables was N plus L plus M plus N. Here we have the number of equations increased by P plus Q and number of variables increased by P plus Q. Now, in these equations we have not explicitly written these terms like u0, I mean the terms like u0 psi x and the stress resultants like N M V in terms of the approximations. If we put the approximations, then finally each equation comes in terms of the unknowns like A0, unknowns like AUJ, AVJ, AWJ, A psi xj and A psi yj. And so this leads to a set of linear simultaneous equations by solving which we can find out all the unknowns, and then from that we can calculate back our solution u0 v0 w psi x psi y. So, we can write solving or u0 v0 w psi x psi y with these double dots nx, ny, ns, mx, my, ms, and we have vx, vy written in terms of the approximations for u0, v0, w, psi x and psi y. So, those 5 set of equations, 5 set of equations which is total L plus M plus N plus P plus Q equations are in have A u j with j going from 1 to L, A v j with j going from 1 to M, A w j with j going from 1 to N, and A psi x j with j going from 1 to P, and A psi y j with j going from 1 to Q. So, these equations have these as unknowns. And by solving this we can find this out, and then we can back substitute in our expression for these quantities, I mean approximations for these quantities, and that gives us the desired solution. So, Here if I number them, so set of equation 1, set of equation 2, set of equation 3, set of equation 4 and set of equation 5. So, if B matrix is 0, that means laminate, symmetric and inertia coupling neglected, then we can solve the last 3 equations separately. In that case, sets of equations 3, 4, 5 can be solved separately. For free vibration, for transverse free vibration or transverse deflection problem, transverse static deformation due to transverse load. Otherwise, if these couplings are present, then we have to solve all the 5 equations. So, this is how the problem is formulated if we have the first order shear deformation incorporated. So, as we can see, the approach is exactly same that we followed for the classical laminate theory. Only thing is that we have to deal with 2 more variables, psi x and psi y, and accordingly the definitions of moments and normal forces have changed. So, this brings us to the end of this lecture. Thank you.